Hi, this is the next part of our capacitor. Today we're going to look at capacitor network. Capacitor network is actually quite the same as a resistor network because when you connect up capacitor in different arrangement, we have to know how to calculate their value, just like resistor, right? Except they are the opposite, right? So the first capacitor network we're going to look at is series connection. Okay, series connection. Let's assume we have 3 resistors. Okay, we start with a battery. Let's say the battery has an EMF of E, and then we have 3 resistors in series. Okay, 3 resistors in series. All their values are different. I call C1, C2, and this is C3. Right? Now, since they're in series, just like in resistor, their current will be the same. So, current is actually the rate of flow of charge. So that means in the same amount of time, the charge accumulated on each plate must be the same. So I'll call this one Q1, Q2, and Q3. I'm referring to the positive charge. So if you refer to the negative charge, there will be negative Q1, negative Q2, negative Q3. And the requirement is your Q1 is equal to Q2 and must equal to Q3. Okay? Even though their plates are different in size and their capacitance value are different. So the purpose of series connection in capacitor network is we want to reduce the capacitor network as much as possible. So the purpose is to change this into this, okay, into the one here. So we have the same battery, and then we need a single capacitor to do the job of the 3 capacitors up here. All right. So if you want a new circuit to function the same as before, there is something that must stay the same. In this case, the charge must be the same. So I'll call this one Q. Okay. So this Q must be the same as the one that passed through all of them. Alright, so we have this capacitance value. New one we call equivalent. Okay, and under the same battery, so these two must be equivalent so that they function the same. So to do that, we know something is that this one must be the same as Q1, Q2, Q3. Because in electronic circuit, if one of the parameters are not the same, then it is not equivalent. Alright. So one thing for sure here is we cannot start from this equation because they're not going to give us any clue about here. But if you look at the circuits, the original one, we have something that in theory that we know that if you measure the voltage across all the capacitor, you're going to have V1, V2, and this one V3. And we know one thing, if our battery does not have internal resistance, we can actually have this. The battery EMF must equal to the voltage across V1 plus across this one and across the third one. Okay, and from here we refer this one to the second diagram, we refer this one to the first diagram. And we know from our definition for capacitance, our capacitance is actually the charge over the voltage across a capacitor. So here, refer to this one. The voltage is equal to the Q over C. Okay, the Q over C. So this one will be charge over C equivalent. Okay, charge over the equivalent capacitance. And the same thing happened to V1, V2, and V3. This one will be the Q1 over C1, Q2 over C2, and the Q3 over C3. And since all the Q are the same, we can actually cancel them. So finally, we have something that looks simple like this. Okay, and of course, we start with only 3 capacitors. But if you have more than 3 capacitors, your equation can be extended theoretically to any number of capacitor. There's no limit actually. There's no limit, but of course in practical there are certain limit because there are some induction problem inside the capacitor. Alright, so that is the formula for series connection. Okay, so series connection is opposite to the parallel connection of it's the same as a parallel connection for resistor. Okay, so if you remember resistor network calculation, you just need to make it opposite. That is how you do it for capacitor. Alright, so the next one we're going to look at is the parallel connection. Okay, the parallel connection, that is number 2. Okay, our parallel connection, we have also the same battery, but we have 3 capacitor in parallel. Yeah, this is C1, C2, C3, and the charge here will be Q1, Q2, Q3. But now the charge will be different. Okay, the charge is different because the charge has the ability to flow around. Depends on the value of the C1, C2, and C3. But one thing for sure is their voltage must be the same because they are all connected to the battery directly. So the voltage here is V1, V2, and V3. So we know that the E is equal to V1, equal to V2, equal to V3. So we want to replace this one so that it becomes something as simple as this. Only one battery and one capacitor. Okay, the battery EMF E, and then the capacitance is C equivalent, and of course the charge will be Q. Okay, the charge will be Q. So we know that all this, if you compress them into one capacitor in parallel, their surface area actually are combined. So when the surface area are combined, we actually accumulate all their charges. Okay, we accumulate all their charges. So that is how we start from there. Okay, so the first part just now, when they are in series, we start by using voltage. But this one here, because they are accumulative, so the Q are actually summing up. Okay, so the Q is again using from this formula. Okay, so we have a second diagram to this side, and then for here, first diagram for the right hand side of the equation. So our Q here is equal to CV. See, CV. Okay, but this is our equivalent capacitance, and then here will be CV1. This one is C2V2 and C3V3. But since their voltage are the same, oh sorry, this one is E. Okay, this one is E. But since their E and V1, V2, V3 are the same, we can actually cancel all of them. So finally, we have this parallel connection for capacitor. This one is C1 plus C2 plus C3. And again, we repeat, this is the 3 capacitor system. But if you have more than 3, you can actually sum up to any unlimited number. So this is our general equation. Alright. So that is the capacitor network for parallel and series connection. Alright. So next one will be energy stored in capacitor. Okay, energy stored in capacitor. The actually main purpose is to store charge, and then when the charge is released, they do work, and that is where the energy comes from. So if you talk about a device, we start talking about energy, is actually meaningless. Okay? Okay. The last part of our capacitor is the energy store in capacitor. But our energy stored in capacitor, we have actually two types. One is just simply energy stored, how much the total energy stored in the capacitor. The second one is the energy stored per unit volume, which is called the energy density. So if we look at the first one, total energy stored. Okay, total energy stored, we can actually use the EC. Okay, energy stored for capacitor. Okay, EC. So the formula is given. Okay, we don't derive the formula. The energy stored is equal to half CV squared. Okay, half CV squared. So C is a capacitance. Your V is the voltage. Okay, V is the voltage. But we can also change the formula to some other thing, depends on what we are given. For example, we know that C is equal to Q over V. So we can replace this one. So it becomes half Q over V, V squared. So finally, you have this, half QV. So you have one equation, you have two equations, you have another one, okay, which is related to C and Q. Okay, C and Q. So that one we're going to replace the V. So the V is Q over C squared. Okay. So when you square this, you're going to have this cancel by 1. So you have half Q squared over C. Alright. So that is a 3 equation that we can actually use to calculate the energy stored inside a capacitor. Now the energy stored as the other type of energy, the unit is joule. Okay, the unit is joule. So this one just tells us how much total energy can be stored inside the capacitor. But sometimes it's more useful to talk about how much energy that can be stored by the capacitor per unit volume. Okay, the purpose of using energy per unit volume, which is called the energy density, is so that we know if you are given a certain amount of space, okay, you can put in, you can cram in how much energy for the capacitor. That is more useful because sometimes if you are asked to design, you as a scientific engineer, you are asked to design a system, you are given, you are allocated a certain amount of space, so you need to know what is the best capacitor option that you can have. Alright? So that is the second one we call the energy density. So here I will use EC, small e and c. So our energy density is actually the total energy stored divided by the volume of a capacitor. Volume of capacitor. What is the meaning of volume of capacitor? Now, you remember our parallel plate capacitor. Okay? This is our parallel plate capacitor, which is connected to positive negative. In between, we have volume. Okay? How much space in between them is what we call volume. Okay? And since the distance here, or we call the separation, is D, and the surface area is A, our volume, I use this V so that is you don't get confused with this V. This is voltage, this is volume. So the volume in between the space here is the surface area multiplied by the separation, which is the AD. Okay? AD. So this one can give us another formula which is very useful when you are asked to calculate the electric field in between the parallel plates. Okay, this is where we start. Energy density is equal to total energy stored. We use this formula, half CV squared divided by the volume, AD. Okay, AD. So from here, we split the C. Okay, our C is actually epsilon naught, epsilon R, A over D, and then we have voltage square divided by AD. Now, what do you get? This one we can cancel. See, we can cancel the A. No more. And then this one combined. So we have this. Half epsilon naught, epsilon R, voltage per separation D. So if you look carefully, voltage per unit distance, that is the electric field. Electric field squared. Okay, so you see our energy density is directly proportional to the square of the electric field. That is a formula to calculate our energy density. But of course, you use this one if you are given electric field, or else you can use this one if you are given the voltage and the separation, or you can actually use this one, or the first one. You calculate the total energy stored first, and then divide by the volume of the capacitor. All right. So the energy density, our unit for energy density will be joule per unit volume. Okay, joule per unit volume. So that is our energy stored in capacitor. One for total energy, one for energy density. Okay, thank you.